Okay. Good afternoon, everyone. And today we have the pleasure to have Dr. Linglong Kong from University of Alberta to be the speaker of our webinar today. And Linglong is a professor at the Department of Mathematical and Statistical Science at University of Alberta. He is the Canada Research Chair in Machine Learning, Fellow of Alberta Machine Intelligence Institute. And Linglong's research area include high-dimensional and neuroimaging data analysis, statistical machine learning, robust statistics, and quantile regression, AI, and for smart health. So without further ado, let's welcome Linglong, and the stage is yours.
Thank you, Jiha, for the invitation, and thank you, everybody, for joining this talk. So today I'm going to share some of my recent research on reinforcement learning, mainly focusing on exploration and optimization. In particular, I want to share my experience as a statistician, how we can contribute to the field of statistical learning and data science. So first, I will give some brief introduction about reinforced learning, and then I will share two projects. One is using distributional reinforced learning to efficiently do exploration. The other one is kind of related to optimization using this dumped understand mixing to accelerate the calculation and the computation in deep reinforcement learning. And then I will also share my experience while doing this research in statistical learning and data science. So what is reinforced learning? Reinforced learning is quite different from the other learning we usually do. And when I started to do this statistical learning, I was told there are three fields, and supervised learning, unsupervised learning, and then the third one would be this reinforcement learning. So what's a typical situation for the reinforcement learning? And we usually have an agent, and this agent can take actions in an environment, and then this can for the action the agent take, we can have a reward. And once the agent taking action, then the environment gets changed because you interact with the environment. Then this all will feed back into the experience of the agent. And through this process, this iterative process, the agent face a certain environment, we call it state, and then they taking action, get a reward, and the state get changed, then you can take action again. And through this interaction and the rewarding process, the agent can learn. And they can possibly find the optimal solution in order to maximize the reward. So the whole purpose is trying to maximize a sort of usually a numerical reward. As the this environment, usually we would model it through a Markov decision process. Usually we call it MDP. This MDP include these following important things. First one is a set of environment and agent state. Usually we use S to represent. And facing different state, we can take action. We can take different actions. So we have an action set A. And you're taking action at certain state, then the state got to change. And there are multiple possible of change of state. And for each state transition, we have a kind of probability. You're facing certain state, you're taking action, then you get an immediate reward. This reward can be stochastic or deterministic. So we have this reward function R, A, S, S prime. Now, I think most of us know this reinforced learning probably through this famous Go game, right? And this AlphaGo. So for this AlphaGo, the objective is we surround more territories than the opponent using this player's zone. In this case, in this setup, the state is every board configuration. Okay, this 19 by 19 crossing. Then the action is where do we put the stones? The reward, eventually reward, either you win or lose. Of course, in certain situations, we can have tie. Now, in reinforced learning, that is a very famous game setup. We call it Atari game, and this is a very old game. And I think when I was a kid, we still have a chance to play this kind of game. But nowadays, this is very old. We use this very old game to mimic this reinforcement learning environment. So this objective in this game, there are about 50 games in this Atari game series. We wanted to complete the game with the highest score. Okay. The state is this raw pixel input of the game status. The action we can take left, right, up, and down, and so on. Then the reward would be, we have a score increase or decrease at each time step. Now, for this reinforcement learning, there are certain basic elements. The first one, like we said, the agent. We have the nowadays some people call it intelligent agent. Okay, it could be a people, and also it could be a machine. So this agent is taking interaction and learn from the previous experience. It's including this reward and transition, and trying to make decision by choosing certain policy. And what kind of policy? It could be deterministic. It's a map for a certain state, you get certain reward, or it could be stochastic policy. Okay, you have that's a probability map from state to this reward. For a policy, if it maximizes the immediate reward, then we call it greedy. If a policy maximizes sort of long-term reward, we call it optimal, and usually we denote it as this pi star. Sheldon, you have a question? Okay. Now, the second element is sort of discounting factor. Well, okay, discounting factor. A greedy policy, because you only maximize immediate reward, right? Usually, it's unlikely to be optimal because it's too myopic. And but on the other hand, like a human being, we need to take future rewards into account. And how to do that? And this is a very difficult mathematical question. So the way we do it is we introduce this sort of discounting factor. Okay, discounting factor. In this setup, the immediate reward R is considered to have full value. And the other reward depends on how many time units away from the immediately, we can have a discount factor gamma. So at nth time units away, we would have a discounted value gamma n times R. And then in this reinforced learning, that's one important concept. We call it the Bellman equation. So after we introduce this discounting factor, we can define this long-term discount discounted value, which is defined as this one, the expected value of this long-term reward, And as most of us as statisticians, we know with this discounted factor, this infinite summation can have a finite value expression. Otherwise, without this discounting factor, this is very hard to deal. So after we introduce this sort of Q function, we have two things. One is for a particular policy, we would have this equation. And for the optimal policy, we also have this equation. So this equation is called Bellman equation. The first one called a Bellman equation. The second one called optimal Bellman equation. Why this Bellman equation is so important? Let's have another look. If we have this optimal policy pi star, we plug in this optimal policy pi star, we find this kind of equation. And based on this, we can define a map from this Q to this expected value. And after we study it, we find this operator T actually can be a contraction map, and under some very mild conditions. This is very important because for this contraction map, we can find a fixed point. Okay, this contraction property provides a very efficient way to find this optimal Q value. Therefore, we can find the corresponding optimal policy, right? And of course, we can see this from this this property from the arbitrary policy. We apply it on this Bellman operator, and it will eventually convert to the optimal policy. Now, there are many approaches to this reinforced learning, and the one based on this Bellman equation is sort of value-based reinforced learning. And for the value-based reinforced learning, we estimate the optimal value function, and then we find the corresponding policy related to this maximal value function. We call it optimal policy. Of course, we can directly search for the optimal policy. This is called policy-based reinforced learning. And we find that the policy achieving the maximum future reward. And a third class is called model-based reinforced learning. For example, we can build a model to mimic the environment. And therefore, we can plan, for example, using this look ahead, using this model. And nowadays, we after this deep learning, we can also have this very active area called deep reinforced learning. For the deep reinforced learning, the key thing is we use a deep neural network to represent the value function, the policy function, or this model. So for deep reinforced learning, it's related to all these three kinds of classical methods. As for the application, there are many applications for reinforcement learning. For example, for this gaming, we all know this AlphaGo, and it can be the best human being in Go game. And also we can have this robotics, so we can use reinforcement learning algorithm to train a robotic. And for healthcare, for example, we can use reinforced learning to deal with sort of a dynamic treatment regime. And I think last year or 2 years ago, there's a paper in Nature using this reinforced learning to deal with this COVID-19 test policy. We have limited resources, and how do we do the COVID-19 test? And we can also do the marketing things, for example, real-time bidding. And some of you may also know this, for example, DD using car dispatching. It's actually a kind of a combination of offline learning and online learning. And we can also do this imaging processing, for example, to do segmentation. And this imaging processing, sometimes it can be better, even better than sort of a supervised learning. The key thing for the success of this image processing is sort of related to ensemble learning, because reinforcement learning can ensemble some weak learner, and eventually we have a strong learner. And for recommendation system, for news recommendation, or this for this purchase online shopping item recommendation, and so on. That's a lot of application of this reinforcement learning. Now, how I get into this, I think that's about 4 or 5 years ago. I got tenured, and I was thinking, what would be my next step? And at the same time, I think most of you know this book, An Introduction of this Reinforcement Learning. The author, Rich Sutton. We live in the same community, and every day he often running in front of my house. So we get a chance to talk, and he said, Linglong, and you are a mathematician, right? You are applied mathematician, and probably there are a lot of mathematical questions in reinforcement learning, and probably you can, help us to solve some of the problem. And though he give this his new book, and that's when I started to do this reinforcement learning. Now, let me introduce the first project. The very first project I did using on reinforcement learning area. So for the traditional reinforcement learning, okay, the Q function is purely based on expected value of the expected mean of the value of long-term return. Well, expectation is good. There's nothing wrong with it. But you usually, as a statistician, let's put it this way, we all know this mean cannot characterize the full distribution, right? And for example, we have this button, and we can have a random reward if you press this button. The mean reward is $1. Then shall we press it? And it seems you press it, that you would get $1. But as a statistician, we know, in this situation, we should be cautious, right? The mean reward, that means, you need to press many times, or many people press it. So let's have a look at one possible underlying scenario, okay? We don't know what's behind the reward. We could have, let's say, case 1, you press, you get $1. This is a good situation. We also could have this case 2, okay? You press, you have probability 99.999% to lose $10,000. But on the other hand, you could win. Okay, if you win, you'll be the rich person in the earth, but the probability is 0.001. So now the question is, let me ask you this question again. Do you press this red button? And probably you don't want to press it, right? Because the reward is high, but the risk is very high, and the risk is very high. So what do we do in this situation? The key thing is, if we want to exploit the environment by just maximize the expected mean, can be very risky in certain situations. Then, as a statistician, we think about, can we characterize the whole distribution of the reward? The answer is yes, but how do we do that? How do we do that? Okay, let's first start some basic concept in distributional reinforced learning. Okay, previous, we have this Q value, which is expected value of this long-term reward. Now we don't take expectation because we want to learn the whole distribution. So we have this Z function. Okay, Z function. This Z function is just the summation of discounted reward. It is a random variable, right? It is a random variable. This random variable also has some good property. It can capture some intrinsic randomness. It's coming from immediate reward, stochastic dynamic, and possible stochastic policy. Okay, and after we define this sort of Z function, then we look at this Bellman equation again. The Bellman equation becomes this two. Okay, and previous the Bellman equation is deterministic, but now it's all random. Okay, this is a random equation because that is a random variable. This reward R is also a random variable, and this one is the same. And we don't even know what's the policy looks like. This pi star. Now, those equations we call it distributional Bellman policy evaluation operator. And then to study this distributional Bellman operator or distributional Bellman equation is more complicated. Okay, and because now it's a random. Okay, and for Bellman equation, one important thing to do this value iteration is it's a contraction map. It's a contraction map. But what about this distributional variable? Distributional variable. It's more complicated. And before we even study it, one natural thing is how do we measure the distance? Okay, because now we have a random variable. Previous we have a determinist value, so we actually have different ways to measure distance between two random variables. It turns out some of the measurement, the distributional Bellman operator would be contraction map, some are not. So the possible choice of this distance, we could have Kramer distance, what's the standard distance, KL divergence, and the total variation. And as you can see, I colored them with different color. The blue one, the Kramer matrix and Western matrix can guarantee this distributional Bellman operator is a contraction map. Well, this KL divergence, total variation, this Euro distance we use in statistical learning, and they are actually not contraction map. Why A1 is taken to maximize this? This A1 just a random notation. You can use some other notations. It's just a notation. Okay. Now this distributional reinforced learning can characterize this entire reward distribution, and under certain distance, it also a contraction map. It seems a quite powerful tool. Then what can we use it? And in the first project, we trying to use it to study to this sort of exploration and exploitation dilemma. What kind of dilemma it is? Exploration is we trying to acquire new knowledge, like we always say keep curiosity, right? As a human being, then you're trying to explore new things. This is exploration, okay? And on the other hand, this exploitation is aiming to maximize profit using known knowledge, And we learned something already, and within this domain we learned already, we try to maximize our profit. And for example, we have a agent where we are playing a sort of three-armed bandit. And for the bandit 1, we get $1 reward. Bandit 2, we get $2 reward. And then if you know this already, then what's next? What would you do? Okay. The known knowledge is bandit 1, $1, bandit 2, $2. The unknown is bandit 3, we don't know. Okay. And if for exploration, maybe we would try this bandit 3. For exploitation, we use our known knowledge, which is try bandit 2, we get the maximum reward on the knowledge we know already. But which one is the right way to do it? There's no absolute correct answer about this, but there are some partial answers. For example, we can use noise policy, okay, or called exponential grading, or we can use optimism in the face of uncertainty, for example, using UCB or optimistic initialization. And also another way to do it is maybe direct estimate the information value, which is very hard, But anyway, in general, all these methods are leading to the agent will be more random, reckless, and curious at early stage. And agent being less random, cautious, and less curious at a later stage. Okay, it's pretty much like human being. And when you are young, you try this, try that. When you are old, you get used to this, to that, then you don't want to try new things. And so, like we said, a naive approach to do this exploration would be we use a variance, okay, and we estimate the variance of the distribution, and we use it as a bonus. For example, if we have the multi-armed bandit environment, if we have 10 arms, for each arm, the reward follow a normal distribution with mean mu k sigma k. Then in this 10 arm sort of multi-armed bandit situation, and we can pick up this action to maximize this reward, the mean plus c times sigma k. Okay, sigma k, we use it to characterize the variation. Mu bar k is the estimated mean, estimated k. Then we can take the action to maximize this. However, this naive approach is not optimal. It's not optimal, and because for the environment, it's actually have different uncertainty. It coming from this. It includes this sort of parametric uncertainty, which is coming from your model, from your method. Also, intrinsic uncertainty. It may be coming from environment or coming from the reward function itself. Well, if you use sort of a naive exploration method, you will always cannot explore this intrinsic uncertainty. So what do? We actually use a sort of decaying bonus. And we use this sort of decaying bonus to suppress the intrinsic uncertainty. So this is the paper, this is the project, the very first project I did in reinforcement learning, and it is published in ICML 2019. So what exactly did we do? And statistically, it's very simple. And you may feel like I can do this, probably, and you can do even better than me. So for this sort of optimism in the face of uncertainty, we only explore this upper tail variability, because this upper tail related to the high reward is more relevant than lower tail. So we only look at this sort of upper tail. Now, how do we do that? We use a sort of left truncated measure of the variability. We call it sigma plus square. Okay, sigma plus square. On the other hand, you remember, for this exploration at the beginning, we want to explore more, right? So that we would be able to learn more. And later we got more and more information, and we don't want to explore that more, because the optimal policy we have and the technology we have might be close to the optimal already. So we introduce this sort of decaying scale. So put this all together, we have this decaying left truncated variance called a DLTV. So this sigma plus square is sort of a left truncated variance, and this CT, which you see square root log t over t, and we use this to introduce this decaying schedule. Okay. So let's see whether our approach works or not. It turns out, on average, our approach achieved about 483% average gain in this cumulative reward on the set of 49 entire gain. Okay. So we gain a lot. And this is, under the condition that we didn't do the fine tune for each game, and we can gain more if we tune each game. We fine tune each game. And also now the learning curve exhibit a sort of plummeting behavior. And also for some hard game, we can even do better. For example, for this Ventura, Private Eye, Montezuma, Revenge, and the Sequence. And this is one of the situations. As you can see, the median human normalized score, which is quite high than this sort of QRDQ. The QRDQ is sort of a benchmark. How did you test the LTV on the entire game? And how long did the test take? And it's a very good question. We look at this median human normalized score to see, whether our exploration scheme can reach higher score faster than this baseline QRDQ. How long did the test take? It takes, quite long. And for each game, it's probably take, but let's put it this way. We actually did all these 15 games. It's probably take, at that time, take 1 to 2 months. Basically, we develop our methodology. We put it on cluster, and then it takes about 1 to 2 months. And what kind of hardware and software? So first, this Atari game is developed by some intelligent people. This is in reinforced learning, we call it simulator. Okay, because in this situation, you can have this environment. You can have the result. You can evaluate the score and so on. So this Atari game is kind of a simulator platform. A lot of reinforced learning algorithm use it. Of course, there are some simple situations. And what kind of hardware? We use GPU cluster, and I forgot the exact setup, but at that time it's the best we can afford. Now we use this. I think my lab have 3 clusters. One is this processor 3090. The other one I kind of forgot. Now it can be a little bit faster. What kind of criteria do you choose for an application example? Because in reinforced learning, this Atari game is quite it's like a benchmark. Okay? It's like a benchmark. And also you can see for this paper, we didn't do any theoretical development. We only developed our method and run it in this Atari game. We can beat other method, then this is good enough. And the proposed method is very interesting. I have a question on what's the difference in relation between proposed method and energy-based. This method basically is fall into this UCB framework, and the difference is how we find the upper bound. We're actually using distributional reinforced learning. In a sense, when we evaluate this secant plus square, we need to learn about we need to use the upper tail of the distribution. We learned 200 quantiles, and we only use that part above the median, and that's why we call it left truncated variance. And another particularly interesting application of this distributional approach is sort of driving safety. This DLTV learns significantly faster than DQN and QRDQN, and therefore it can achieve higher reward for safety driving, because we all know in this safety driving, the time is very important. As you can see, our framework can quickly get very high reward, while this QRDQN and the DQN is way slower. This is very important. Well, for these projects, the lesson we learned is, exploration is very important. We should be optimistic in the face of uncertainty, and using decay helps a lot. And the truncated measure can help us stabilize the process. And we combine these two frameworks together, and we have a very efficient exploration method. This is the first project I want to share. Now, let me go to the second project. As you can see, and also some of you asked this question, how long does it take and what kind of software? We use the best available GPU cluster. It's still very slow. And if you check the paper, as you can see, and the time we repeat this learning process, it's only a couple. And this brings the issue of this reproducibility crisis. Like, for example, before this AlphaGo. And when we first developed this sort of TD learning, sparse coding, those kind of method in reinforcement learning, usually we repeat the simulation like 100 times and even 30 times, and at least more than 10. At that time, as a statistician, we feel quite comfortable, right? But after this DQN was introduced, and this is sort of a deep reinforced learning, and they repeat the time consuming, the possibility we repeat the simulation is very low. For example, DQN only repeat 5 times. And the AlphaGo only, there's no repeat, only once, okay? And some other benchmark, for example, later on this Rainbow, Mo0, and so on, they only do the simulation once. For us, for this exploration paper, we only did it 5 times. Why? Because we cannot afford to run the, like I said, with the BIOS machine, we can afford. We need like 1 to 2 months. Okay, and if we want to repeat, let's say 100 times, that would be several years, and that's not possible. So how do we deal with this situation? And this is a very important issue in reinforcement learning area field. One thing is we can look at a small scale environment. Atari game, although it's a very old game, it's popularized in 1970s, 80s, but it's still too complicated for this reinforced learning. So we actually developed this sort of mini Atari game environment, and you can run this environment way faster. And but on the other hand, what about we develop fast algorithm? Can we do that? The answer is yes. This is also the motivation for our second project. Okay, let's first go back to look at this Bellman operator. For the Bellman operator, the Bellman operator is a contraction map, right? It's a contraction map. The whole point is to find this sort of fixed point. Okay, now therefore we have this fixed point iteration, and the optimal value function essentially is a fixed point of the Bellman optimality operator. Now, for the existing reinforcement learning, we try to find the fixed point. Usually it's slow, and also it's related to the sample inefficient. And can we make the algorithm faster? The answer is yes. There is some effective multi-step interpolation method. For example, Anderson mixing. Okay. However, this method only heuristically be applied in reinforcement learning. Like the first project we did, we developed this. We say, okay, we can do this exploration using this left decade, left truncated variance. And here, some people did this experiment using Anderson mixing and said, okay, the Anderson mixing can improve this convergence. But I remember the reason I get into this area. I'm a statistician or applied math. I want to, understand the mathematics. So this Anderson mixing actually is lake of this rigorous mathematical justification. So we're thinking maybe we can have a look at this question. And so this is another project we did called Damped Anderson mixing for deep reinforcement learning, acceleration, convergence, and stabilization. This was published in NeurIPS last year. Now, let's have a closer look. What do we do? And we actually provide a deeper insights into this AA algorithm and see why it can be fast. We build a connection with this Quasi-Newton method. Okay, we find okay, this AA algorithm actually is kind of a quasi-Newton method, so that's why it can be, faster. And the second contribution is that we actually proved, okay, this AA mixing can increase the convergence radius, and within a actual contraction factor, it's not only faster but also converge faster. And then another thing is, even in the empirical experience, the previous researcher found it's not that stable. Okay, and well, it's not difficult to understand because this is sort of quasi-Newton method, and quasi-Newton method works under certain conditions, and so we propose a sort of stabilized procedure so that the algorithm can be stable. So this is the three contribution we did with the with this project. Let's do it one by one. The first, let's look at the Anderson acceleration algorithm. Okay, previous we have this Bellman operator, and we have this Q function. Previous, we only use information from the last step. Well, Anderson acceleration use the information from previous M step. We actually use a sort of a linear combination or optimal linear combination. So here is, we have this M previous estimate. We do a linear combination. This alpha I is some weight. So this weight follows, we optimize this one to get the weight. You may think, oh, in order to get a weight, you need to do another optimization. This might be, we want to be faster, this might be slow. It turns out we can have this, after some mathematical calculation using this KKT condition, we can have this analytic solution of this optimal coefficient. So we don't need to do this optimization through coding. So it won't take much time. Now, the question is why this process can accelerate. The reason is it's related to sort of quasi-Newton method. And how to make this connection, we need to rewrite how do we get this optimal alpha k. As you can see, previous this alpha k get a sort of constraint summation equal to 1, and we can, and this is a very typical trick for us, right? And we can reduce one number of parameter, then it becomes an unconstrained problem. So we did that, and after that, we rewrite this Q value updating. And it can be written as the QK plus 1, the K plus 1 step, as QK step minus some learning. Well, this part, it turned out gets the format of this one, gets the format as this one. Okay. Why it can be, why it can accelerate? The reason is this GK can actually serve as an approximation of the inverse Jacobi matrix of this EK. So in sense, this part contains certain information or partial structure matrix information about the real inverse of Jacobi matrix. Without this part, actually, it's just a beta Ki. This would be the exactly the Q value function iteration without this acceleration. Well, in this AA algorithm, it actually have this extra term using some partial information from this inverse of Jacobi matrix. And therefore, it can be fast. So this is the first contribution we did, we actually found this understand this AA algorithm actually is kind of a quasi-Newton method. That's why it worked. Now the second thing is, how good it is, and to do that, we look at this convergence rate analysis. And we have certain assumption. For example, we need the derivative assumption. We need the first derivative bounded, second derivative bounded, and so on for this Bellman operator. Under this condition, okay. Under this condition, we find okay, the EK, the error at less than or equal to CK times this one plus this and plus this plus this. This is a sort of a little bit complicated inequality, but if you look at the first term actually characterizes an increased coverage radius because this extra contraction factor CK. But we don't like this third term and second term and third term. So in order to have a better understanding of this sort of convergence rate, we add some further condition. The further condition is we assume this operator is a gamma contractive contraction map. So under this condition, we can actually get better result, and the second term and third term can be absorbed into this format. And therefore, we can clearly see, okay, this increase convergence radius. And we actually provide this sort of convergence guarantee of this AA on this reinforced on this RL. But unfortunately, we impose condition assumption 1, assumption 2. Unfortunately, the regular Bellman operator doesn't satisfy those conditions. This max operator is not even differentiable. So what do we do? Now, one trick to deal with this kind of situation is using this soft max operator to replace this max operator. But it turns out that this soft max operator only satisfies the first condition. It's differentiable, but it's not a gamma contractive. It's not gamma contractive. And at that time we start there, we feel like, what do we do? And then we look at the literature, we find, okay, we are not the first one to looking for this gamma contractive. And some people already look at this question, and they have this mellow max operator. Mellow max operator actually satisfy assumption 1, assumption 2, both conditions. So let's look at what's this mellow operator. This mellow max operator is defined as this one. The good thing about this mellow max operator is it's differentiable. Also, it's not expensive to satisfy all the conditions we have. And therefore, our framework now becomes we replace the Bellman operator by this mellow max operator. And then we can achieve increased convergence radius. Now we look at the third question. The third question is a stabilization curve. And most of us are statisticians, we know for this kind of thing, if we want to stabilize, one trick would be we add some, R2 regularization. So here is the way we do it. We add a R2 regularization for this weight. and to make it stable. So that is the extra part we add in order to get this K. But on the other hand, we know if we add L2 penalization, then it will introduce bias. Fortunately for our situation, it turned out if the algorithm converges, then this part will eventually disappear. So if the algorithm converge, this third K its norm will go to 0, at K go to 0. Therefore, when converge, the regularization term will vanish, and we will get the exact Anderson acceleration result without the stable regularization. This is very, it's like a free ride, not very good. So with this stabilization, we can have this updated algorithm. This GK tilt becomes this one with this part as a regularization, And also we prove this why it can be stable and compare with the regularized one with the non-regularized one. And I'm not going to go to detail. And another comment I want to say is the Mellowmax operator certifies this differentiable and non-expensive property, and therefore it can be faster and get this better convergence rate and so on. The softmax operator, it only certifies this first condition, but in practice it still works. And if you recall the empirical version of this Anderson accelerator, they actually used this Bellman operator. So in other words, the Bellman operator sometimes also works, even though it doesn't certify any of those conditions, assumption 1 and assumption 2. So that's the, this theoretical guarantee and empirical experiments. Okay, this is a summary of our stable AA. We do two parts. One is Mellowmax operator. One is stabilized weight. And here is the experiment. Experiments, we provide some experiment to show that we indeed have this fast convergence and a significant improvement. And we look at the Dueling DQN as baseline, the black one, and Dueling DQN with naive acceleration, and Dueling DQN with our stabilized and also max Mellowmax version, which is the red one. As you can see, it can, sometimes this this naive AA doesn't work. Sometimes it works, but our method always works. And we also did the experiment to show that only this Mellowmax sometimes doesn't work, and we also need this stable regularization. And so this our framework, this stabilize and the Mellowmax, they actually have this joint benefit. Okay, I think pretty much that's all on my talk. But I also want to share with you about my experience with this reinforced learning. I started this area in 2018, and this is almost 4 years. At the beginning, there only I actually didn't know much statistician working on reinforced learning, but I feel there are a lot of areas our statistics can contribute in this area, and nowadays I gradually find some people, statisticians, are working on this area. I feel very very happy, and I hope if you like this area, please also do some contribution on this important area. Okay, I guess this is all of my talk, and I'm looking at this QA session, trying to look at some questions, and yeah, and the first question is in healthcare, and we don't have this randomness, and do you think we could use an inverted DLTV to push the agent to be? Yeah, I think we could use this DLTV potentially to make better choice. But on the other hand, in clinical trials, there are many constraints. It's quite challenging. Let's put it in this way. But potentially we could do that. Yeah. Especially we can learn the reward distribution. Maybe we can, like you said, like in the first project, we pick this left side, and we can also pick some quantiles. And we did another project. We only look at some sort of in reinforced learning. That's we can use option to help us to do exploration. Yeah, we sort of the reason we use the R2 norm is the penalty we put over that when converted, it get vanished. If we use the R1, it's basically incurring sparsity. And the sparsity in reinforced learning also being studied in some situation, but usually when we select feature, we select X, maybe, I think one of my colleague from CS at U of A's, Masa White, she did something using this R1 penalty. And for us, we use R2 here. The key thing is when, it convert, that part get vanished. What are some open questions in distributional reinforced learning? Yeah, there are a lot of open questions. I think one of my one important question is, most of the time distributional reinforced learning works better than reinforced learning, but why? And I think one of my students write a paper trying to answer this question, but it's only partial answer. And if we can learn in what kind of situation we the distributional reinforced learning would be better than reinforced learning, that would be great. But it's a very hard question. And also, how to use this distributional reinforced learning to do certain things. Even Rich Sutton agreed, this distributional reinforced learning would be a great novel area in reinforced learning. I think the author who developed this distributional reinforced learning and trying to have a book on this, distributional reinforced learning. You can have a look at the book. You just Google distributional reinforced learning, and maybe you can, find more open questions from that book. The imaging processing process basically you need, because reinforced learning is quite different from supervised learning and unsupervised learning. You need to have this action, reward, you need to set up those kind of things. And for imaging processing, for the image segmentation processing, people basically, set up some middle reward. So the reinforced learning can gradually learn to improve the segmentation. maybe in each step they can improve different area or different using different feature to improve it. Eventually, it may reach the effect of ensemble weak learner to a strong learner, and there are a couple of papers to using this reinforced learning to do image segmentation. Yeah, you can check it out. Thank you.
Thank you very much, Linglong. Let's stop recording and move to the Q&A session.